If you've ever built something with LangChain that worked perfectly in your notebook, but completely fell apart in production, you're not alone. Today, we are going beyond the simple pipe operator to uncover 5 architectural patterns that separate toys from production-ready AI systems. Let's dive in. Here's where every developer's journey starts. On the left, we have our beautiful development environment. Everything works. Your Jupyter notebook runs perfectly. The chain flows smoothly from input to output. Every test passes. You're thinking, this is easy, ship it. But then production happens. Look at the right side. Same code, different reality. Network latency spikes freeze your application. The LLM decides to ignore your carefully crafted formatting instructions. JSON comes back malformed. And suddenly, your entire system grinds to a halt. This gap, this reality gap in the center, is where most AI projects fail. The difference isn't about writing code, it's about architecting for chaos. Because in production, chaos isn't the exception, it's the baseline. So how do we bridge this gap? That's what the next 5 lessons are all about. Let me show you something most developers miss entirely. That pipe operator you've been using, it's not just syntactic sugar. It's the visible edge of something much more powerful, the Runnable Protocol. Look at the center. This hexagon represents the language that every LangChain component speaks. And it gives you 6 core methods organized in 3 pairs, each solving a different production problem. First pair, invoke and a-invoke. These handle single inputs. Think one user asking your chatbot one question. Synchronous when you're prototyping, asynchronous when you need that response time under 200 milliseconds in production. Second pair, batch and a-batch. These process entire lists at once. Perfect for that nightly job analyzing 1,000 customer reviews or scoring hundreds of support tickets for urgency, all in parallel instead of looping one by one. Third pair, stream and a-stream. These return results chunk by chunk. This is how you keep users engaged while the LLM thinks, showing them text as it generates instead of a blank screen with a spinner. Now here's the brilliant part. Because every component implements the same interface, your prompt templates, your models, your parsers, they all snap together in ways that get you closer to predictable and composable than anything we had before. And this unlocks 2 composition patterns. Runnable sequence. That's your pipe operator flowing data linearly. But the real power? Parallel. This lets multiple operations run simultaneously on the same input. Which brings us to the first thing you need when you build on this foundation. A system that doesn't fall over when the LLM misbehaves. Let me show you the difference between code that crashes and code that adapts. We're looking at 2 paths here, and they couldn't be more different. Top path, standard parsing. Data comes in, hits the parser. Is it valid? If no, boom, red X, exception thrown, application crashes. Your users see an error page. That's it, game over. But look at the bottom path. Same data, same parser, same validation question. But when it fails, instead of giving up, something clever happens. The retry with error output parser catches that failure and builds a correction prompt. It takes 3 things: the original prompt you sent, the faulty output the LLM just produced, and the specific error message explaining what went wrong. Then it sends all 3 back to the LLM and says, essentially, hey, Here's what you were supposed to do. Here's what you actually did. Here's exactly what broke. Try again. Now, important caveat, this isn't bulletproof. If your prompt was fundamentally unclear or the LLM lacks the capability for the task, retrying won't magically fix it. But for formatting errors, minor omissions, and syntax mistakes, this catches the majority of real-world failures. And because LLMs are actually pretty good at fixing their own mistakes when you give them context, you get that green check mark far more often than you'd expect. This isn't just error handling. This is teaching your system to learn from mistakes in real time. That's the difference between brittle code and resilient architecture. Here's a question. Why is your AI application so slow? Let me show you something that might hurt a little. Left side, synchronous execution. You need to run 3 independent tasks: sentiment analysis, topic extraction, entity recognition. Each takes 1.5 seconds. Simple math says 4.5 seconds total. But look at these gray blocks. Those represent your application. Just sitting there, doing nothing, waiting. Your CPU is idle. Your users are staring at a loading spinner. And all because you're running tasks that have no dependencies on each other, one at a time. Now look at the right side. Asynchronous execution. Same 3 tasks, but this time we use asyncio.gather or runnable parallel, and boom, they all run at the same time. Total execution, 1.5 seconds, 3 times faster. Now, important qualifier. This assumes the LLM provider can actually handle concurrent requests. Most can, but if you're hitting rate limits or your provider queues requests server side, you won't see the full 3x improvement. Still, even with some rate limiting, you're talking 2x or better in most production scenarios. And LCL handles the async plumbing automatically, even for components that weren't built async first. Bottom line, synchronous code in production is leaving massive performance gains on the table. Stop waiting. Start parallelizing. Now that we've made it fast, let's make sure it's actually returning correct data. Let's talk about something I call data hallucinations. Not the factual kind everyone worries about, but structural ones. When your LLM returns something that looks reasonable, but violates your schema in subtle, dangerous ways. Look at the top. Your LLM is supposed to return a product rating, but instead you get rating 6 when your scale only goes to 5, or rating 5 stars. That's a string, not a number. Or rating null, missing data entirely. Now, if you're just using string parsing, maybe some regex, you're in trouble. Any one of these could slip through, corrupt your database, break your analytics, and give your users completely wrong information. But here's where Pydantic becomes your shield. Look at the center. We define a strict schema. Rating must be an integer, and it must be between 1 and 5. That's it. Now watch what happens. Rating 6 hits the shield. Rejected. Out of range. Rating 5 stars hits the shield. Rejected. Wrong type. Expected integer. Rating null. Rejected. Missing required field. Only valid data, the green check marks, make it through to your database at the bottom. And here's the beauty. When Pydantic catches these errors, it doesn't just say validation failed. It gives you specific, actionable error messages. Value must be between 1 and 5. Expected int, got string. You can log these. You can trigger retry logic. You can alert your monitoring system. Pydantic isn't just parsing, it's enforcement. It's your last line of defense against structural errors poisoning your production system. But even with great validation, complex chains can still be hard to debug. Let me show you how to make the invisible visible. Here's the situation every developer hits. Your chain is doing something weird. Data is leaking between calls. Some component is failing, but you can't figure out which one. And you're stuck adding print statements everywhere like it's 1995. But what if I told you your chain can actually show you its own architecture? Look at this. On the left, one method call, chain.get_graph.draw_ASCII. That's it. And what you get is this, a complete visual map of your entire computation graph. Here's your prompt template at the top. Data flows down to this runnable parallel node. And look, it branches ahead. LLM call 1 and LLM call 2 running simultaneously. Now watch how the callout boxes give us real architectural insight. Parallel execution point. That's where we know concurrency is happening. Potential state leak. That's a warning that these parallel branches might be sharing mutable state, which is exactly how you get race conditions in production. Retry logic branch. That's where our error recovery kicks in. Everything converges at the parser, goes through retry parser as a backup, and finally reaches output. This isn't just documentation. This is debugging by sight. You can see where data transforms. You can spot bottlenecks. You can verify that your parallel branches aren't crossing streams. Complex systems don't have to be black boxes. Make your architecture visible. Make it debuggable. One method call. All right, let's bring this all together. This is what a production-ready LangChain system actually looks like. Center stage, your core pipeline. Input flows through prompt engineering into the LCL pipeline built on that we talked about, through the LLM, and out to your user. That's your happy path. But notice what surrounds it. 5 protective layers: async parallelization, retry with context, Pydantic validation, graph debugging, and error recovery. Now look at the bottom. On the left, that thin green line, that's the happy path, the scenario where everything works perfectly. But look at all those red dashed lines on the right. Those are the unhappy paths, the real-world chaos we talked about at the beginning. And notice, every single one of those unhappy paths is being caught by one of our protective mechanisms. Network issues, caught. Bad data, caught. LLM failures, caught. Nothing reaches your users unhandled. This is the fundamental shift in mindset we've been building toward. You're not just writing code anymore. You're architecting systems that behave predictably under chaos. The prototype was never the problem. Staying in prototype mode is. And now you know exactly what separates the two: error recovery, parallelization, validation, visibility, and composition. Stop chaining, start architecting. If you found this valuable, hit that subscribe button. We're building more architectural deep dives like this. Drop a comment below. What's your biggest challenge building production AI systems? And remember, master the engine, not just the steering wheel. See you in the next one.